In this lesson, we are going to learn how to find the derivative and the limit of vector functions. So let's say with this vector function that I have on the screen here, okay, which has the following component function, which is s of t, y of t, and then z of t. Okay, if you are asked to find the limit of this function, let's say the limit as t approaches t naught, okay, for this vector function here, okay, this will be equal to the limit as t approaches t naught, okay, for the component functions x of t, comma, y of t, and then z of t. Okay, so this is how we write it. Okay, so one thing about computing limits of vector function is that you can compute the limit of each of the component functions. So you can write this as the limit as t approaches t naught for x of t, comma, the limit as t approaches t naught for y of t, and then the limit as t approaches t naught for z of t. So you're going to compute the limits for each of the component functions. So that's how to compute the limit of a vector function. So let's take an example. So let's say you have the vector function given to be cosine of t. Okay, that's the first component function. Then you have sine of t divided by t. And also you have the last component function to be t squared plus 2. So you have to compute the limit of this vector function here. So that will be compute the limit, okay, as t approaches 0 for this vector function. So in doing this, you are going to have the limit as t approaches 0 for cosine of t, comma, sine of t divided by t, and then t squared plus 2. This is what you have now. So you're going to find the limits of each of the component function. Okay, so I'll take this to be x of t, I'll take this to be y of t, and then I'll take this to be z of t. So let's find the limits of each of the component functions. So I'm going to have the limit as t approaches 0 for the x of t, right? And then that would be equal to the limit as t approaches 0 for cosine of what? T. Okay, so for limit, you can try substituting the 0 inside and see if you get an answer. So that will be cosine of 0. Okay, and then this will give us 1. Okay, this will give us 1. Let's take note of this. So that would be the limit for the first component function. Okay, so let's do same for the second component function, okay, which will be the limit as t approaches 0 for y of t. Okay, this will be equal to the limit as t approaches 0 for sine of t divided by t. Okay, so let's try direct substitution here. So that's going to give us sine of 0 divided by 0, that's division by 0. Then you're going to get 0 on 0, which is indeterminate. So you must find a way to compute the limit. In this case, you can find the limit by using L'Hopital's rule, okay, where we are going to differentiate the term on top and then the term down here. And then after that, you try substitution again to see if you can find the limit. So in this case, we're going to find the derivative of sine t. So we're going to have the limit as t approaches 0. Okay, when I differentiate sine t, that gives us cosine of t. Okay, and then when I differentiate t, that gives me 1. So let's try direct substitution again. We're going to have cosine of 0 divided by 1. Then that gives us 1 divided by 1, which is equal to 1. So that will be the limit for the second component function. So let's do same for the last component function. So that will be the limit as t approaches 0 for z of t, which will be equal to the limit as t approaches 0 for t squared plus 2, okay, for this function here. So let's try direct substitution. So I'm going to get 0 squared plus 2, and then this will give us a value of what? 2. So that will be the limit for the third component function. So now I'm therefore going to write the answer. Okay, so I'm going to say that the limit as t approaches 0 for the vector function of t will be equal to, you have the first component function's limit to be 1, and then the second also was 1, and then the third was 2. So this will be the answer after you computing the limit of this function that was given. So for a better understanding, let's try our hands on another example. So you take another example. So let's find the limit as t approaches 0. Okay, for this vector function here, we have at minus 1 divided by t. Then have the second component function to be the square root of 1 plus t minus 1 divided by t. Then we also have 3 divided by 1 plus t. Okay, so we have this vector function. So you have to find the limit of this vector function. So let's look at what is going to happen here. So let's take this to be x of t, and then let's take this to be y of t, and then this to be z of t. Okay, so now let's find the limit of each of the component functions. So we're going to have the limit as t approaches 0 for the x of t, okay, which will be the limit as t approaches 0 for e to the power t minus 1 divided by t. Okay, so let's try the substitution here. We're going to have e to the power 0 minus 1 divided by 0, right? Then any number to the power 0 is 1, so I'm going to have 1 minus 1 divided by 0, which will give us 0 over 0, which is indeterminate. So we must find a way to compute the limit. So to do this, you are going to apply L'Hopital's rule here. Okay, so you are going to differentiate the term on top and then the term at the bottom. So let's do this. When I differentiate, okay, let me write this here again. We're going to have the limit as t approaches 0, then I differentiate the term on top. When I differentiate exponent t, I'll get exponent t, and then when I differentiate minus 1, I'll get 0, and then when I differentiate t, I'll get 1. So we're going to have the limit as t approaches 0 for e to the power t, and then when you do the direct substitution, you're going to have e to the power 0, which will give us a value of what? 1. So that was for the first component function. Okay, we got 1. So let's do for the second component function. So we are going to take the limit as t approaches 0 for y of t, okay, which is equal to the limit as t approaches 0 for this function here, square root of 1 plus t minus 1 divided by t. Okay, when you try direct substitution, you're going to get 0 on 0, which is indeterminate, so you must find a way to compute the limit. Okay, so to do this, I'm going to multiply the whole expression by the conjugate of the numerator because of the radical that we have there. Okay, so I'm going to have this to be the limit as t approaches 0 for the square root of 1 plus t minus 1 divided by t. Okay, multiplying, let me write this again, minus 1 divided by t. Okay, multiplying the conjugate, so that will be 1 plus t plus 1, okay, divided by square root of 1 plus t plus 1. So now let's do the simplification. When you multiply the terms on top, okay, which is this term here by this term here, it is the same as me squaring these terms here. So to perform the multiplication on top, I can square this term here and then I can square the one too. Okay, so when I square this term here, this two cancel the square root and then the square of one is still one. So we are going to have the limit as t approaches 0 and then we are going to have 1 plus t minus 1, right? Divided by t multiplying square root of 1 plus t plus 1. Let me extend this a bit. So over here, we see that we have 1 and then minus 1 here, so they will cancel out. So we are going to have the limit as t approaches 0 for t divided by t multiplying the square root of 1 plus t plus 1. Okay, so this t will cancel out this t. We are going to have the limit as t approaches 0 for 1 over the square root of 1 plus t plus 1. So now let's try the direct substitution again. We're going to have 1 divided by the square root of 1 plus 0 plus 1. And then let's look at what you are going to get. So you are going to have 1, okay, divided by the square root of 1 will be 1. So you are going to have 1 plus 1. That will give us 1 over 2. So that will be for the second component function. Let's write this here also. Okay, so now let's consider the third component function, okay, which is 3 divided by 1 plus t. So for that one too, you can try direct substitution. Okay, so because of space, I'm going to write it straightforward. So that will be the limit as t approaches 0 for 3 divided by 1 plus t. Okay, so let's do the direct substitution. So I'm going to have 3 divided by 1 plus 0, and then that gives us 3. That's for the limit of the third component function. So we have this here. Okay, so now let's write our answer. Okay, so we are going to have the answer to be equal to, because of the space, so I'm going to just write the answer there. So I'm going to have 1 comma 1 on 2 and then 3 as the answer. So that will be the solution after computing the limit of this function that was in here. Okay, so we are going to look at how to find the derivative of vector functions. We are going to learn how to find the derivative of vector functions. So let's look at that also. So let's say you have that same vector function. Okay, so we have the vector function of t, which has the component function s of t, then y of t, then z of t. Okay, so we have to find the derivative of this vector function, which will be d r of t dt, right? So this will be equal to the derivative of s of t, comma y of t, comma z of t, okay, dt. This is what you have now. So what you can do is that you can find the derivative of each of the component functions. So this will be equal to the derivative of the first component function, which will be the s of t divided by the t, okay, and then comma the y of t t, okay, and then we're going to have z of t dt. So it's just like differentiating each of the component functions. Okay, so we're going to take an example. Okay, we're going to use the question you solved previously. Okay, so given the vector function which is equal to dq. Okay, let me use this example rather. I have t cube comma sine of 3t minus 2. sorry, sine of 3t minus 3, okay, divided by t minus 1. Okay, then we have the last component function, which is e to the power 2t. Okay, so let's find the derivative of this function here. So what do we do? We must first find the derivative of each of the component functions, right? Let's take this to be x of t. Let's take this to be y of t. Let's take this to be z of t. So you have to find the derivative of each of these component functions, right? So we're going to have the x of t dx, okay, equal to the derivative of t to the power 3, that will be 3t squared. And then let's do same for the second component function. So we have y of t to be equal to sine of 3t minus 3 divided by t minus 1. We have to find the derivative of this function here. Okay, so we are going to apply chain rule. So I'll set the denominator term to v, and then I'll set the numerator term to u. So we are going to have y prime of t equal to v multiplying u prime minus u multiplying v prime divided by v squared. Okay, this is what you have now. So now we know u, okay, we know u to be equal to sine of 3t minus 3. Okay, and then we know v to be equal to t minus 1. Let's find u prime. U prime, okay, u prime, let me free up some space. U prime will be equal to the cosine of 3t minus 3, okay, times 3. There's no space, so I write this here. That's 3t minus 3 times 3. And then we will find v prime, which will give us 1. V prime should be equal to 1. That's the derivative of t. And then we know the derivative of 1 will be 0. So that's how can I have 1. So let's do the substitution. We're going to have y prime of t, okay, which is the same as dy of t dt. Okay, if you want to write dy of t dt, you can write this y prime that we have here. Okay, so this should be equal to, we know v, right? So that's what t minus 1, and then multiplying u prime, which is 3 cosine of 3t minus 3, okay, and then minus u multiplying v prime. Okay, u is what? Sine of 3t minus 3. Okay, okay, sine of 3t minus 3. Okay, let's manage this here. So we're supposed to multiply by 1, but you know v prime is 1, so you can leave it that way. So you then divide by the square root of v, so that will be t minus 1 squared. Okay, so let me write this here. I'm going to have dy of t equal to t minus 1, okay, multiplying 3 cosine of 3t minus 3, right? Okay, then okay, I think I should take out this brackets. Let's just make this multiplying 3 cosine of 3t minus 3, okay, and then minus sine of 3t minus 3. And then it's just 1 here, so you just leave it that way. Divide by t minus 1 squared. So that will be the derivative for the second component function. So now let's consider the third component function. But before then, let me draw some rectangle around this so that you can see them. Okay, and how this here. So now let's find the derivative of the third component function. So that will be z of t. Okay. So that will be, when I differentiate e to the power 2t, I will have 2 multiplying e to the power 2t. Okay, so you know that when I differentiate e to the power 2t, I'll get e to the power 2t, then I'll multiply by the derivative of what? This expression here. So that's how come I have this answer here. So now I have all the derivatives that we need. So now let's go ahead and write our answer. So we are going to have the r of t, the t to be equal to the first function, you have 3t squared. Then for the second, we have t minus 1 multiplying 3 cosine of 3t minus 3. Okay, minus sine of 3t minus 3 divided by t minus 1 squared. I'm not sure you can further simplify this here. That's why I left it that way. But you can try and then distribute the t minus 1 to it also. Then we have for the last component function, we have the derivative to be 2 multiplying e to the power 2t. So this will be the derivative of the vector function that was given. Thank you very much for watching this video. Please make sure you like and subscribe.